Okay, this is the slide. Previously, we were here at slide number 12. And now we have to start this slide number 13. And we were seeing different things about different graph models, basically. So we saw already the complete graphs, the cycles, the wheels, and then now the n cubes. N cubes. So basically, if you will draw something shaped like that, so that is a square, but this is basically a cube, actually, in 3D or whatever. So from the title, n cubes, now you can understand that you have to draw some graphs like that. And for n cubes, this n cannot be, for example, it would start from here. It is written n is equal to 1, 2, and 3. So this, when n is 1, it is q1. And for q1, you have 2 vertices. Means normally when you have cube, then that cube normally draws on a concept of 2 raised power n bit strings. Okay. So when you have to draw some graph related to cubes, then that graph will be drawn on the concept of bits. 2 raised power n bit strings, and this n is the length of that bit string. So if you have 1 bit, then what are the possibilities? 0 and 1. So that's why you are seeing here the 2 vertices. That is the reason. Maybe a question arrived in your question already, in your mind already, that why not 1 vertex? The reason is this concept goes with the concept of bit strings. And this is 2 raised power n. And when you have n is equal to 1 bit, then 2 raised power n, it means that you have 0 and 1. Two vertices. So you have to keep 3 to 4 different things if you want to draw an n cube. So you have to keep that information in hand or in your mind, and then you can draw these n cubes. So the first thing is that it will be based on 2 raised power n bit string, where n is the length of that string. So the first thing is you can draw n cubes on the concept of 2 raised power n bit strings. You will give any value to this n, and then you will know that how many vertices are there in that graph. For example, in Q1, where n is 1, put this 1 here, 2 raised power, so you will have 2 vertices. And similarly, for 2, you will have 4 vertices. For 3, you will have 8 vertices, or like that. So this is one thing that you have to keep it in your mind. And the second thing is, in these graphs, when 2 vertices are adjacent with each other, then the difference between those bit strings would be only 1 bit. The difference between the adjacent vertices would be only 1 bit. Here, for example, it is 0 and it is 1. Okay, that is 1 bit. And here, for example, these are the adjacent one. These are adjacent with each other. So this is 0. And here it is 1. So this bit is same and only differ in this 1 bit. Similarly, look at here. This right hand side bit is same, only differ in this left hand side bit. So this is the second thing that you have to keep it in your mind. If you are going to, so the adjacent vertices must have a difference of 1 bit only. Okay, there are 3 to 4 things that you have to keep it in your mind. So now things are coming, for example, the topics which are now coming ahead, these topics will be a little bit complicated, not the simple one as you already have seen in previously. So this is the second thing that you have to keep into your mind up to this point. This is mentioned here. Exactly one bit position. One bit. And these are the graphs Q1, Q2, 3. Okay, these are the displayed in this figure. And one other thing is, you can draw the next, you can draw this graph from that one. You can draw this Q3 from Q2. So in general, I can say that you can draw n plus 1 cube if that you can draw Qn plus 1 from Qn. How? By making two copies of this Qn plus 1. For example, this one, you are getting this one by making two copies of this graph. And after making these two copies, for example, this one is 0. When you will make it, automatically strings will become 3 because you have to cover from 0 to 7. Okay. So that's why it is this bit length of the string is this 3. So this is 0, 1. So this would end 0, 1, 2, 3, 0, 1, 2, 3. So this is at the bottom. Place one copy at the bottom and other copy at the top. And join their vertices. So this is the thing that you have to keep in your mind. So you can get your next Qn plus 1 graph from the previous Qn by making copies of the previous one, by making two copies of the previous one. And here you can see in the bottom we have this one, and at the top we have just two copies. So this is the third thing that you have to remember in your mind, that we can get the next graph from the previous graph by making two copies. And now the fourth thing that you have to keep in your mind is the bottom side. For example, one copy will contain strings starting with 0. So all these are starting with 0 and have the 1 bit position difference. Difference also, the rules are there. And all these bits strings are starting with 1. The first copy has starting with 0, the other copy is starting with 1. I have started the recording or not yet? Yes, Alhamdulillah. So these are the things which I mentioned here. And one in the other copy. So we are now up, you have seen things up to here. So these are the 4 things that you have to keep it in your mind. And for example, Q3 is, this Q3 is constructed from this one. And now you know how it is constructed. So we already discussed. So this is discussed here. And we already discussed that how we form. So when Q3, when you are going to form this Q3 from Q2, okay, you can. And this 3 is saying that your bit string length is 3. So that's why it is 3 at all the positions. So make it one copy at the bottom, other copy at the top, and join all the vertices. And join these vertices with each other, then you have that cube. And here we know that you have to keep bit string starting with 0 at the bottom and bit string starting with 1 at the top. And if two vertices are adjacent with each other, look at the difference. The right hand side, 2 bits are same, only this is the difference. So that rule is also existing there. So this is how you can get the n cube. This is how you can draw the graphs having their label as n cubes. Now we have the definition. This definition is about bipartite. And that condition if that holds in some graph, then that condition would be called bipartition. We will see. If you are given with some graph, for example, like this, if this is a graph and given to you, first you have to divide that graph vertices, the set of vertices, you have to divide the set of vertices into two subsets. For example, suppose you have some graph C6. This is your C6, okay? Displayed in this previous slide, in which you have 6 vertices connected with each other. So now, so this is maybe V1, V2, V3, V4, V5, V6, okay? Now you have divided, you have to divide that vertex set into two vertices, into two sets of vertices. For example, this V1 is first set, V2 is another set. You have to think and then you have to divide it. You have to divide it in such a way that each vertex in V1 will have an edge towards some vertex in V2, not all, okay, some, I'm saying some. This is first rule. And second, that no edge in V1, for example, this one or that one, no edge in V1 will have are adjacent to each other. No vertices in V1 no vertices in V1 are adjacent to each other, and similarly no vertices in V2 would be adjacent to each other. They are not connected with each other through some edge. This is the second thing. And if this condition holds, then you can say that graph, that simple graph is bipartite. So now the definition is simple graph. A simple graph is what? Which does not have the loop or the multiple paths. So a simple graph is called bipartite if its vertex set V, if you have its vertex set for some graph, and if you will partition, means divide. If you divide it into two sets, V1 or V2, like that, such that every edge in the graph connects a vertex in V1 and V2, okay. Those vertices V1 and V2 will have edges in the graph, and no edge in G connects either two vertices in V1 and two vertices in V2. The things. So this is written, the things which I explained already now, these are the sentences which is saying the same thing. So if you have a graph, you have to divide the vertex set of that graph into two subsets. You have to divide in such a way that you will have some edge from this vertex V1 to V2. Actually, after dividing it, you have to draw all its edges according to that graph. Okay, and then you have to see that these conditions are fulfilled or not. You have, after dividing that vertex set V into V1 and V2, you have to draw all the edges which are in the given graph, which are given in the existing graph. You have to represent all those edges which are already there in the given graph. When you represented all the edges, then you will see, okay, you have the edge from V1 to V2, V1 to V2, okay, that's okay. And you don't have any edge between the vertices of V1 or any edge between the vertices of V2. If it is okay, then your graph is bipartite. And this property and this condition for the pair V1 and V2, for this pair, if you have that condition, this is called bipartition. You have bi and partition. You have two divisions. Bi means two. Partition is just a division. So this pair V1, V2 would be a bipartition of the vertex set. So now this these two partitions, bipartitions, uni mean one, bi means two, tri means three, tetra means four, and you can go on like that. So bipartition of the vertex set. So these are the two partitions of the vertex set V. Okay. This the other word is bipartition. Okay. So let's see now. So we have some graphs C6 and K3 in previous slides. Show that these graphs C6 and K3 are bipartite. This is the question. This is the question in example 9. And in example 9, I have only showed that C6 is bipartite and example 10 is K3 is not bipartite. But let's have a look how it is. So C6. This is C6, okay? This is C6. If you will just give them the names, V1, I have an idea, but I don't know it will work or not. Let's see for a moment. I am just stopping the recording. Okay. Now this will not be displayed in the lecture, okay? So for example, now our graph is like that. These are the 6, 1, 3, 4, and 5. 3, 3, 0, 3. Like that. Like that? Close. Yes. Okay. So it is Q, it is C6. So now the question is either it is bipartite or not. So then what I'm saying, just write, label them with some vertices, that these are the vertices. Now you have to divide this vertices into two sets. And there are two rules, you know that. From the set 1, if there is a vertex, that vertex will have some edge to other. You have to draw the edges from this graph. And the other is that no, I can just show you, we can just read that again so that we will not do any mistake. No edge in graph connects either, yes, if you have the vertices here, then no edge will have adjacent to each other. So this is true for V1 and similarly this is true for V2. Okay. So for example, if now you have to, this is a hit and trial method. There is no defined steps in it that you have to do. This is a hit and trial method. You have to hit something. If it is successful, okay. Then you have to hit some other thing. Then you have to see that it is okay. If it is successful, then okay. If not, hit other thing. So that's why it is hit and trial. You have to hit something and trial. So for example, okay, this is V1 now. I'm just starting. So if it is V1, so V1 is adjacent with V2. So it means that I cannot keep this V2 here, according to the rule. So, but this V3, I can keep this here because it is not connected with this one. So, okay, suppose I am keeping this, okay, yes. So V1, if V1 is there, V3 is also the candidate here. Candidate here. I don't know whether it is right or wrong, I don't know. I don't know. But this V1 has adjacent to V2. So it means that I can keep this V1 here and V2 here in this set. Due to that edge. Because I have two rules in my mind.
And I am doing these things according to those rules. So this is connected. So then it should be in different sets. This is what you are doing. V1 here, V2 here. And we have H here. And now this V3 is not connected with V1. Okay, that's fine. So where I can keep this in this V1 set, or in this set, or in this set, just okay. So this is the candidate for here, but I don't know it is correct or not. Okay. And V3 is connected with what? V4. So maybe I can keep this V4 here. I can keep this V4 here. And V3 has a connection with this one. And this V3 is not connected with that one. And V4 and V2 has not connection with each other. But up to now, we are on the right direction. What is the remaining? Okay, V4, V5. So V5 cannot be here in this V4 because they are connected. So I can keep V5 here, then maybe. And V5 is connected with V6. Okay, keep this V6 here. And there is an edge between V5 and V6. I'm looking at this graph and drawing these lines. And now this V1, V3, V5 does not, V1, V3, V5 does not have any connection, direct connection. V2, V4, V6, V2, V4, V6 does not have any direct connection with each other. So both rules are satisfied. You can complete the, for example, you can complete the edges if you want, but this is what we want. Now this is what we want. So V1, V2, V2, V3. So I know that there is an edge here, V2, V3. And V3, V4, okay, already there. V4, V5, V4, V5. And then V5, V6 already there. V6, V1, this one. So now this is completed, but these are the two subsets of the vertex set V. And these are the two partitions of that V. This is called bipartition. And now this graph is called bipartite. This graph is called bipartite. Now, what was the other one? K3. Wallah, where is K3? This one, huh? The triangle. So now we have this K3. Maybe I am saying V1, V2, V3. So if I will keep V1 here, V2 here, V3 is connected with V1, I cannot keep it here, not keep it here. So it's not, you cannot actually complete the process of this whole graph. And V3 and this V3, we cannot put it here, we cannot put it here. When you don't have that option, because it is connected. It is connected also with that one, also with that one. So we cannot distribute it into two sets. If it is the case, then it means that we cannot make their bipartition. And if we cannot make their bipartition, then this graph is not bipartite. It is simple. So, okay, coming back, where is that thing? Stopping video, going to share screen again. I don't know. Recording is going on. Alhamdulillah. Otherwise, it was again an issue. Huh? Okay. Now, example 11. Are the graph GH, this one, G and H, displayed in figure 8, are bipartite, bipartite? So now the same procedure that you have to do. So you can read it by yourself now. So these are the graphs, G and H. Things are written here. I am just saving my time because there is more things which are coming ahead.
And now theorem 4. A simple graph, now again, this is the definition of that theorem. A simple graph. This theorem is saying that you can find the bipartition with some other easy method. What is that method? That method is also again the same, but giving just a different aspect. If you have some simple graph given to you, that would be bipartite. If you will start assigning colors to each vertex, if you will start assigning colors, two colors, you will use only two colors, red or blue or maybe red or green, but two colors. One for V1, other for V2. One for first partition, other for second partition. Okay, a simple graph is bipartite if and only if it is possible to assign one of two different colors. You have two colors, and then you have to assign one color from these two colors, one to one set and other color to other set, to two different colors to each vertex of the graph. So you have to give the color to the vertices of the graph so that no two adjacent vertices are assigned with the same color. That is the same thing. That is not a different thing. It is just coloring. Otherwise, concept is same. But it is theorem 4. And now you have example 13, which is what? Complete bipartite graphs. What is complete bipartite graph? What is complete graph? If you know the complete graph, and if you know the definition from the beginning of this lecture, what is complete graph? In which each distinct pair of vertices will have the edge. Each distinct means different. That is the definition of complete graph from the starting of the lecture. And if that complete graph is bipartite, then you can call that a complete bipartite graph. So anyhow, it is written here that a complete bipartite graph, you can represent that graph with KMN, where this M and N is what? M is representing one subset, N is representing another subset. And these subset will contain vertices, not anything else. Okay? Like, for example, you have seen in bipartition, you have seen that you have one subset and another subset. So same thing is, if you have some graph K, we are using this K for the complete, because C we are already using for cycles. So that's why the letter is different here. M and N. So this M and N is what? These are the number of vertices. But this M is the number of vertices is in one subset. N is also a number of vertices is in another subset. So this graph will, if it is bipartite, it will have two subsets with an edge between two vertices. So after that, respectively, with an edge between two vertices, if and only if one vertex is in the first subset and other vertex is in the second subset. So these are the two subsets. And if you have vertices in M, then you will have an edge, one edge, from that vertex to another. You will have an edge from one vertex from here, from this M, to another vertex here in this M. This is what? Look at this example and then you will understand. For example, this is a complete graph. And what it is? K2, 3. M is 2. and n is 3. So this upper portion, this is one subset. This lower portion is another subset. This is now M, and this is now N. And then you can see that from this vertex, you have an edge to other vertex, an edge, not multiple edges, an edge. So basically, this is what? Distinct pair of vertices. It's the same definition that you have for the complete graph. But you have two subsets. This is the difference with respect to that complete reference, complete graph. Because in complete graph, you must have some edge from here to here. Look at this pointing, where I am pointing. If it is complete graph, if you are not talking about bipartition, then these edges would have some edge, according to the definition of the complete graph. But here, we are talking in two partitions. And those partitions will have their edges complete. So this is M subset, this is N subset. And then from this edge, you will have an edge to all other vertices in the other subset. And from this vertex, you will have will have edges to all other vertices in N. If you have this situation, then you can call that graph a complete bipartite graph, which means that it is a complete according to bipartition. This is also that complete bipartite. This is also, all these are complete bipartite. Look at here, this is the first M, this is the second N, and you have the edges all over there. Yeah. So this is what complete bipartite graph. And it is K2, 3, 3, 3, 3, 5, 2, 6 are written here, are mentioned here. What is subgraph? If you have a graph G, and if you have some subgraph of that graph G, then how you can identify? You can identify that if the vertices in the subgraph also existing in the main graph, and the edges existing in the subgraph also existing in the main graph, then you can say that it is a subgraph of that main graph. I can give you the understanding while standing there in a better way, but I am maybe in the next semester I will not record anything and I will use the whiteboard, etc. That will be better. So anyhow, so if you have a main graph or major graph like that, I am using the word major graph just to distinguish between the subgraph and the main graph. So if you have a graph G with vertex set V and edge set E, then I can call this H. I can call this H a subgraph with vertex set W, edge set F. If W would be subset of this V, if this W would be subset of this V, and if this F would be subset of this E, okay, then I can say that this H would be the subgraph of this graph. And the subgraph H of G would be proper subgraph of this graph G, would be proper subgraph of this graph G when H not equal to G. If you have the main graph and then again showing the main graph and saying it is a subset, then it is equal to that G. If yours, then you can say a subgraph H of G is a proper subgraph when H is not equal to G. By the way, in final exam, you don't have the definitions, but it does not mean that you don't have to understand. G is a graph. Now G is again a graph with vertex set and edge set, and it is simple graph. When it is simple graph, it means that it does not have the loop and the multiple paths. And then subgraph induced. Now you have another term. There would be some subgraph which you will extract from the main graph, but that graph now we will call it inducted subgraph. When there is a term inducted subgraph, it means that that subgraph is extracted from some other main graph, but it has some condition. What are those conditions? Okay, let's see. The subgraph induced, where is the pen? Where is the pen? Okay. The subgraph induced is a verb. Induction is noun. Inducted is again verb. Induce, induct, or you can say induct, inducted, inducted. Induced means extracted, like that. Subgraph induced by a subset W. The subgraph induced by a subset W. So now you will have the subset W of the vertex set V. So for that subgraph, you will have some set W that would be the subset of this V, okay? And okay, that graph will have W and F like you already have before in the previous definition. If the edge set F, this F is what? This is edge set, this is vertex set of subgraph. If the edge set F contains all edges from E, connecting pair of vertices in W, connecting pair of vertices in W. For example, this is a graph, now you will understand. It is saying that this is the subgraph now with this F, which is the number of edges. If these edges are all you have from this E, then that subgraph would be inducted. Then that subgraph would be inducted from that main graph G. This is what this definition is saying. But now you will see. Here you have the graph. The graph G is shown in figure 15, is a subgraph of K5. What is K5? The K5 is given here. This is K5 in the previous slides. Maybe this one. So this is K5. Now we are also given this graph here, and we are asking that this is a subgraph of that graph, or this is a subgraph inducted from that subgraph. Then what? Then you will have the W and F. So you will have those W's, vertex set, and F. F is what? The edge set of the subgraph. And E is the edge set of the main graph. So, okay, it looks like this part, okay? If I draw this one, this is there. All edges of the F, all edges, this one and that one. All edges of F, this is F, edge set, all edges. So we have all edges from this E. Set F contains all edges from E, connecting pair of vertices in W. So this is a subgraph of this graph, but not induced. Why not induced? Because this edge, because these vertices, has edge here or not? They have the edge, this one or some other thing. So this one. So all other distinct edges are connected in this W. So without this edge, this graph is a subgraph of this one, but not inducted graph. If you want to make this thing inducted graph, then you have to also consider this edge also. And when you will consider this edge, which is also existing here, then it will be completely, now you can say that now it is inducted graph. Okay, this is the difference. And now you have seen the application of definition 7 and also 8 in this single example. This is what written here. Subgraph induced by ABCE. So now that thing will be. Okay. Now another definition, union of two simple graphs. If one graph is G1 is equal to vertex set V1 edge V1, another one is G2 and vertex set is V2, edge set is E2, then their union of vertices would be V1 and V2. This is V1. And their union of edges would be E1 union E2. And after doing that, then you can finally say that G1 union G2. Okay, let's see, moving on. Find the union of this graph G1 and G2 shown in here in 16a. So this is figure 16, this is A. And you have this G1 and G2 graphs given here. This is easy. You just have to. Sorry? Yeah, this is what I want to say. You just have to put it logically. You have to pick it up logically and place it over here. Your name is Ryan? Ryan? No. What is your name? No. Karam Dawariz, yes. Yes, yes. So Karam Dawariz is saying the right thing. Pick any one graph imaginary and place it over the other. And don't repeat anything and keep all the things there in the resultant diagram that you have your union. So this is after imaginary combination, you can combine these two graphs and then you have your result. So ABC is also here. And DE, okay, D is here, E is not here. So this square is available there. And this triangle is available there. This triangle is available there. And this one edge in the square, this one will die. So all the edges are there. Union of all edges, union of all vertices. This E was, which was here, not here, but now in the resultant it is available. So after doing the union of vertices and edges, the graph that you will get would be the union of two graphs. So this is simple. And there are some examples, 12, 14, 16, you have to do by yourself. Now, how you can represent a graph? The topic is now changing. Okay, previous and section now started section. We have now started section 10.3 of chapter 10 of graph. So now this is what about graphs and graph isomorphism. The last topic would be this isomorphism. But first is how we can represent a graph. We can represent a graph without multiple edges. We suppose that that graph is a simple graph without multiple edges. Then we can represent that graph if we write down all the edges of that graph on a paper or in a list or something. If we list all the edges, for example, this edge A to B, okay, write it. A to C, okay, write it. A to E, all edges. After representing that edges in the form of a list, this is one way to represent a graph. The other way to represent a graph is with no multiple edges. I'm saying we can represent with multiple, but with no multiple edges. The other way is to represent the graph is adjacency list. That is what we want to study. This is the major topic. Adjacency list. Adjacent, you know what is adjacent. Two vertices are adjacent with each other through that edge. So adjacency list. So that would be some similar to like that adjacency concept. So example 1, use adjacency list to describe the simple graph given in figure 1 here. So represent that simple graph into the form of adjacency list. This is the question. And what is the way? Here you have to make two columns, one for the nodes, for the vertices, other for the adjacent vertices. For example, here in this graph, it is easy. For example, how many nodes you have? A, B, C, D, E. You can just write them here. And then A is connected with which one? With B, with C, and with E. So these nodes which are connected with this A node, because now we are looking at A. We are looking at A. So these other nodes which are connected with this A is called the adjacency of A. Okay. And here you are writing it like that. B, comma, C, comma, E. These are the nodes which are connected with this A. Similarly, this A is connected with this B. This, for example, for D, E and C or CE is the adjacency of this D. C and E. This is easy. This is a simple graph without multiple edges. Now, we have a directed graph here. And it is asked, represent the adjacency list of this directed graph. We have the direction here. So I can ask this same question, represent the adjacency list of this directed graph given here in this diagram, or show all the vertices or terminals which are connected with the vertices in this diagram. I can also say like that. But this is a simple way. But in a technical way, give me the adjacency list of this graph. So then what? A. Okay, for A, this is going on here to B. It is connected. So A is connected with C. This is coming here. So that is not connected. Okay, that is not a connection. Coming. So you have to focus that from A edge is going out to other vertices. That is your direction. So B, C. Here it is D is also there. E is also there. So that's why you can write it then. For B, let's have a look on the B. So this edge is going out. So B to B, that edge you have. And then it is coming inward. So D is also there. So B and D, is there anything else? It is coming inside. So let's have a look. B, only B and E. Okay, it's easy. Moving next. Adjacency matrix. If you have a graph, you can build a adjacency matrix. And if you are given with the adjacency matrix, you can build a graph by looking at that adjacency matrix. So this is a adjacency matrix in the diagram. What it is showing? It is only showing that you have edge from that vertex to that vertex. For example, from A to A, if it is 0, then it means that from A to A, you don't have any edge. From A to B, if it is 1, then it means that you have an edge from A to B. This is simple. So suppose if you have a graph G with set of vertices, set of edges, if it is a simple graph, why simple? Because we don't want to go into complications. We want to understand the concept first. So that's why I always taken simple graph. And where size of V is equal to N, and if the vertices in this V are from V1 to Vn, because size of V is N vertices, then the adjacency matrix you can represent with A or A of G, which means adjacency matrix of this graph G. And it would be N cross N. If there are 5 vertices, it would be 5 cross 5. 5 rows, 5 columns. And it will contain 0, 1 as entries inside it. 0 and 1. If it is containing 0 and 1, it is adjacency matrix. If it is containing some other digits, it is similar to adjacency matrix, but it is now representing something different. We will see. So use an adjacency matrix to represent the graph shown in so graph is given to you and asked for use adjacency matrix. Use the concept of adjacency matrix and draw that adjacency matrix. So normally these things are not the part of adjacency matrix. I have just displayed here for your understanding, to keep these things logically in your mind. So in this graph, how many vertices? A, B, C, and D. Okay, A, B, C, D, A, B, C, D, A, B, C, D, rows and columns. And from A to A, we have vertex here? No, we don't have any loop. If there is a loop, then it is 1. But we don't have any loop, so it's a 0. A to B, we have edge? Yes, so it's 1. A to C, we have edge? Yes, it is. We have an edge, so it's 1. D to D, we have edge? D to D, we don't have loop, so it is 0. Okay, D to C, we have edge? D to C, we don't have any edge, so it's 0. So this is how you can build the adjacency matrix, nothing else. Now, we can draw a graph if we have this adjacency matrix, or if this adjacency matrix is given, we can also draw a graph, or from the graph, you can draw this adjacency matrix in both ways. Yes.
I can represent the directed graph. A connected to B, B is not connected to A. So that I know it's
yes, you can go on like that. Now, here we don't have 0 and 1. We have multiple paths. We don't have the simple graph. We have the pseudo graph. What is pseudo graph? The definition, which will have the loops and the multiple paths. Yeah, you can call it simply a graph, but it is a pseudo graph. So now in this graph, you have multiple paths. So, okay, no issue. ABC, consider it is here. So A to A, you have loop? No, so that's why it is 0. And A to B, how many paths? 3. Write it there. A to C, you have here something? No, we don't have. So that's why 0. A to D, we have 2 paths, so write it like that. And now here, B to A, this one, B to A, again you have 3. Write that 3 there. So that is the thing, nothing different. And these are the trade-offs. Trade-offs between adjacency list and adjacency matrix. you can say the attributes of adjacency list. What are the positions? What are the situations in which you have to use adjacency list? And what are the situations where you have to use the, what was the other thing? Matrix, adjacency matrix. So when your graph will have few edges, if your graph has few edges, and if you make, what it means? It means if you draw the adjacency matrix, it will have many zeros in that because the edges are not too much. So when you have many zeros in the adjacency matrix, that is called sparse. Okay, that is a probability. This is a term that we normally use in probability theory. Anyhow, so when your graph has few edges, don't use adjacency matrix. You can use simply the adjacency list. You can use simply the adjacency list when your graph does not have too much edges. But if your graph is dense, what it means? Your graph has many edges. And if you will make, for example, then in that situation, if you have many edges, then okay, use the adjacency matrix. That is something written here, nothing else. Moving next, what is incidence matrix? We have the graph V and E. I'm not saying what this V and what this E is, you know that. And if it is an undirected graph, suppose that these are the vertices of that graph from V1 to Vn, and these are the edges of that graph from E1 to Em. Then the incidence matrix would be, this is N is the last vertex, M is the last edge. Then the incidence matrix would be the ordering of vertices and edges. And it would be N cross M. So incidence matrix would be, the order of that incidence matrix would be N cross M. So these are the number of rows, these are the number of columns. Okay. So the incidence matrix would be N cross M matrix, and we can represent it with M, and it will contain these entries Mij. And these entries will be 1 when you have edge from Ej, when you have edge Ej is connected with vertex Vi. When you have this edge connected to this vertex I. When, for example, currently you are here, for example, maybe, for example, okay, this is the diagram. So currently you are here. If it is connected with this V2, so this is the next. So this edge is connected to this previous V1. Okay, this is what he's saying. Because some edge will go from that vertex. So if that edge is there, you can represent it with 1. If the edge is not there, you can represent it with 0. It would be a adjacency matrix like thing. Represent the pseudo graph given. So we have the figure 7 here. So this is the pseudo graph. Have loops and multiple paths maybe. Write its incidence matrix. Okay, here you don't have to write vertices and vertices. Here it is different. N cross M. N is for vertices. So first vertices. So this N is for vertices. This is rows. So V1, V2. How many vertices you have? 1, 2, 3, 4, 5. So V1 to V5 is the vertices. And then you have to count the number of edges. How many edges in that graph? Here we have 8 edges total. So from E1 to 8, these are your columns. Okay. Now this is different from the previous one. And then now you can see from V1, you have this edge E1 from V1. We have this edge E1. Okay. Represented with 1. Because this is something we said in the definition. From add this V1, we have this edge E2. Okay, look at it in the graph. We have this edge E2. Yes, represented with 1. So wherever you have 1, represent it with 1. Wherever you don't have any edge, represent it with 0. And this is the incidence matrix. Now, this is the last topic. But still we have 3 slides. Isomorphism. Isomorphism is something which is, the other meaning is similarity. Isomorphism means similarity. For example, this is the graph. You will be given 2 graphs, and then it would be asked that show that these 2 graphs are isomorphism, are isomorphic. Then it means, okay, in easy way, you can say that the question is asking about the similarity of the graph. The graphs are similar to each other or not. But let's see the definition. You will find different definitions at different places, because there are more than one way to prove this isomorphism. If you are given with 2 graphs, G1 and G2, and those graphs would be isomorphic if there would be a one-to-one and onto function exists from this V1 to V2 with the property. Now some other condition. This is one condition. And the other condition, with the property that A and B are adjacent in G1. It is saying that if there are 2 vertices which are connected with each other in graph 1, then it would be, then their function, after applying this function, f of A and f of B, then after applying this function over them, the whatever that value you will get for AB, those values would also be connected or adjacent in G2. In G2. Then you can call that your graphs are isomorphic. And this property is called isomorphism. The function that will hold now, that would be called isomorphism. Let's see this example. And if this property is not existing in that graph, then it is, the opposite is called non-isomorphic. Now example 8, show that this graph G and H given in figure 8 are isomorphic. This is easy, okay? This is easy, so that's why. But these questions will become complicated as you go forward. If it depends on the graph actually. If the graph given to you is easy, then the question answer is easy. Otherwise, it's not easy. So this question is solved according to this definition. So you have to, if you are given 2 graphs, then you have to start with, you can start with any vertex, okay? It is again hit and try. Maybe, yeah, let's see. So suppose you are going to start with U1, okay? And then you have to find its equivalent vertex in this graph. That equivalent vertex can be V1, can be V2, can be V4, can be V3, any. In short, you have to find the similarity in this graph and that graph, that they are similar. Their diagram is different, but maybe they are similar. Let's see. So we can start with, okay, we are going to start randomly. You can start with any, but we are going to start without wasting time. We are going to start with U1. If it is U1, you have to find its equivalent in graph H after applying the function. After applying function over U1, suppose you are saying that the image of this U1 is V1, suppose. Why you are saying, okay, this U1 is connected to this U2, and this U1 is and this vertex has degree 2, this vertex has degree 2. So this V1, okay, this is connected with this one, degree 2. This is connected with this one, okay, degree 2. So this V1 can be equivalent to that U1. So if you say that f of U1 is equal to V1, and then f of U2 would be what? Here, U2 and U1 are connected. You have to find vertex for U2. Now we are vertex for U1 is final, that is V1, okay? This is kind of bipartition, but you have to find the similarity. Now we are working on this U2. For U2 is connected with U1, okay? U2 is connected with U, and here, which one? This one is connected with V1. We have to find the similarity. Isomorphism generally means similarity. So that's why, okay, for f of U2, I am giving V4. Because this V4 is connected with V1, and then this U1 and U2, which is connected here, then V1 and V4 connected with each other. So it looks like similar to that one. Okay, so for f of U2, you can say that I am assigning V4 from that graph. And then for U3 is connected with V1, and this V3 is connected with V1. And U3 is also connected with V4. V3 is also connected, okay, connected with V3 is also connected with V2. Condition holds. So for U3, okay, for U3, we are taking this V3 and V4. Okay, according to similarity, what is 1 to 1? 1 to 1 means that from if you have two sets, then for sets, for B, you have at least one from here. You can have, or if I will go from left-hand side to right-hand side, for all elements of that set A, you will have at least one here in that B. So this is what you have one here from that set. For you, you have one here from that set. Okay, so 1 to 1 correspondence is there. But it doesn't mean that now it is isomorphic, okay? You have to check more. This is only one thing here. We just said that 1 to 1 and on to. When you have 1 to 1 and on to, then it means that for set A, you have one element here. And also on to means one element here. So 1 and 1 only, 1 and 1 only. It means, so 1 to 1 correspondence is there. But there is some other condition. Adjacency is not checked yet. You have to take some pair in graph 1. If they are adjacent with each other, they must be adjacent in G2 also. So that is some kind of similarity you have to find. So here in the graph, and how much similarity U1 and U2 are connected with each other, U2 and U4 are connected with, so this is what you have to check. In graph G1, you have U1 and U2 connected, U2 and U4 connected, U3 and U4 are U3 connected, U3 and U4 connected. So all these connections, now you have to check. Here and also same here, because now you have given the images here. We have the images for the domain now. I don't know you are understanding or not. If I say you have the images now for the domain. What is domain here? This is your discrete structure knowledge. What I should have to say now? What is domain, codomain, image, range? Anyhow, leave it because I have few time and too much slides. If set A and set B is given to you, set A is domain, set B is codomain. And if you assigned elements from set B to set A, that is, you have the images for the elements of that A. Okay, if you are not worrying, I am also not worrying. So what are the adjacent vertices in G? U1 and U2. U1 is connected with U2, U1 is connected with U3. This is U1 and U2, U3, U2 and U4, U2 and U4 are connected. I'm just writing what are the connected pairs in G1. And if these are the pairs, then what are the images that you have for these pairs in H, U1 and U2? What is U1? V1, U2, V4. So V1 and V4 should be connected here, and they are connected. You can check now like this. And then what? What is the next pair? U1 and U3. U1 is what? V1. And U3 is what? V3. U1, V3 should be connected here. U1 and V3. So what is that one? What is the next pair? U1 and V3. And what is their respective images? V1, V3. So V1 and V3 are connected here. Okay. And in this way you can go on. And when you will find all these adjacencies there, then you can say, okay, G and H are isomorphic. Okay. Similarly, they must have the same number of nodes or vertices. Yeah, that is needed. They must have same number of vertices and same number of edges. Then they can be similar, then they can be isomorphic. Otherwise not. If, for example, if some question you will have like that, first, the easy thing is to count their number of edges and vertices. If they have different vertices and edges, then there is quite a chance that they are not isomorphic, non-isomorphic. But still you have to check some one or more further condition to give your final answer. For example, here, I will do this one and the next one is with you. So show that graph displayed in figure 9 are not isomorphic. So these graphs, this is the figure 9, graphs are given to you. And it is being said, show that these graphs are not isomorphic. So now these graphs are not isomorphic, okay? This is a book and this is not making fun with you, okay? This is not a teacher who is making fun with you. So it is now not isomorphic. They are non-isomorphic graphs, but now you have to prove it that they are not isomorphic. Now the number of vertices, okay, now check it. 3, 2, 5, 5, okay, and so 5 vertices are equal. Edges 3 and 3, 6 maybe. 3 and 3, 6, yeah, 6 equal. Then maybe you will thinking about that it is isomorphism, isomorphism is there, but actually not. So this is what I said, that things will go to complications when you will move forward. Anyhow, then what? Count the number of degrees here. This is also a way. Counting the number of vertices, counting the number of edges. But now you have equal vertices, equal edges, but it doesn't mean that now it is full and final isomorphic. No, they are not. So now the next thing is, now we are counting here in the first step, we are counting the degree of each vertices. A has degree 2. Here, in this H, you have one vertex E with degree 1. But here, you don't have any vertex with degree 1. And what it means, let's have a look over here. The graph H, which will have the degree 1, this edge E. So based on degree, you can also conclude that they are not isomorphic. This is now another new thing that you have learned from the previous example. You can count the degree and then you can identify that is there anything which is different. Maybe we have the edges with 2, we have the edges with 2, okay. We have edges 3, we have the edges, this one with 3. But this one edge, which has the degree 1, but we don't have any degree 1. So this is what we are saying, that in G and H, in H, we have a vertex which has the degree 1, which is not existing here. So that's why we are saying that. And if it is degree 1, and E and D are connected in in graph G, and when you have to find the isomorphic, you have to find their adjacencies also. So here E and D are connected, but here it is not. So that is only one point is sufficient to say that it is isomorphic according to the definition. Because previously we were finding all these adjacencies here, equalities, similarities. This is the second property of that definition. If something is adjacent in G1, must be adjacent also in G2. So here E and D are adjacent, and here E and D are not. So due to that condition, we can say that it is not isomorphic, this pair ED. Now, determine whether the graph shown in figure 10 is isomorphic. Now this one, figure 10, these are the graph G and H. Show or determine that these graphs in figure 10 are isomorphic. So now they are isomorphic. You have to show. It can be not. You have to show. There the question was different. Show that the graph displayed in figure 9 are not isomorphic. That question is saying that they are not isomorphic. You have to show. Yeah, you have to show why. But here determine, you have to determine by yourself whether the graph given in figure 10, the graph which is given in there, is, when you have the word whether, it means both options are possible. Both options are possible in English. When you have this word whether. I don't know the Arabic word, but in my language, I know the words. So now these are the vertices. Okay, check their vertices. How many vertices? 4 and 4, 8. 4 and 4, 8. How many edges? 4, 4, 4, maybe 10 edges, and 4, 4, 10. So edge, number of vertices, number of edges is same. Then the other thing is degree. Okay, look at there. Maybe we will find something which is not there. We have the edges with degree 2, we have the edges with degree 2, we have the edges with 3, we have the edges with 3. Is there anything which is not there? Okay, we cannot even identify anything from these degrees. So in both G and H have 8 vertices, 10 edges. Both have 4 vertices of degree 2 and 4 of degree 3. In both the graphs, you have 4 nodes with degree, whatever, 2 and 4 with degree 3. So still we are not finding anything which is making these two graphs non-isomorphic. So this is just a sentence I have written here. This is not available in the book. Still conceivable. So still it is just convincing us that it is isomorphic. From the information that we have collected now up to this point, this information is just convincing us that this is isomorphic. But let's see what is the thing here. So moving on. So degree of A in G, this one, this vertex, the degree of A in this graph G is what? 2. Degree is 2. And if I will find some vertex for this A, I have to find the images. I have to find the images in H. So what would be the images? The degree with the vertex with degree 2, because it is a vertex with degree 2. So what would be the possible images in H? The vertices with degree 2, the same thing. You have to find the same thing. So this T has the degree 2, this has the degree 2, this has the degree 2, this has the T equals 2. So these are the candidates now for the images, for the image of this A. For the image of this A, but I don't know. So, okay, and this vertex A is connected with vertex having 3, okay? You have to find the adjacency. This is second property. So these are the candidates. From these candidates, so that A is connected with what? Connected with such vertices which have the degree 3. So if T is the candidate, it is connected with this vertex degree 3. If U and this T is connected with the vertex which has a degree 2. So this is violence. This is violence because the image of this A would be such a vertex which must be connected with degree 3. So if I am giving this T as an image that is connected with this 3, okay, but it is also connected with degree 2. So that is violence. So T is now gone. So can it be U? So U is 3 connected with this 2. So U is also gone. X is connected with this and it has the degree 3. That is also gone. So no, it is connected with this 2 actually. That is also gone. And Y is connected with this 2. That is also gone. So now you have a bigger point, huh? Now you have a big point now. The students who are understanding, they are enjoying. But the students who are not understanding, they are sleeping and they don't care. Okay? The students who are enjoying, the students who are understanding, they are enjoying these things because these are the puzzling type things. Anyway, yes.
Vertices have like similar, so if it's not the same, it's not.
Yeah, it's not isomorphic. That is isomorphic. This is what I have given you the meaning generally in the beginning. So these were the candidates that we found in the H. But then we have seen the things, and everywhere there is a violence. And these are the only candidates. The rest of the nodes are not the candidates. And if you don't have the candidates left, that means you don't have adjacency. So now this is a proper evidence that G and H are not isomorphic. There is something, another way is also mentioned here. That way is saying that, okay, so this is some subgraph. These are the vertices which have the degree 3. Which have the degree 3. This one, and that one. And they are forming this graph here, this shape. They are forming this shape here. Now focus on all vertices with degree 3 and make a shape for this, from this graph also. So this vertex has degree 3, this vertex has degree 3. So this is only an edge like that, D and H. This vertex has degree 3, this vertex has degree 3, it is only showing an edge like that. And this shape is different from that shape. So this is also a way to identify that they are not isomorphic. Okay. So this is discussed here. And next is, again, you have to identify G and H are given, and you have to identify that they are isomorphic. Do it by yourself. And here you, at the end, this adjacency matrix are given to you to find the adjacency. You know that we can find the adjacency. So this is also discussed here in the solution of this. Rest of the things are same, but some extra information is given to you that if you want to find the adjacency of those graphs, make the adjacency lists, matrix. And if that matrix is same, then it means that adjacency is same. And then you can decide it quickly. So nothing else. And these are the example 4 and 6 in the chapter that you have to do by yourself. Now it is the end. And any question in this lecture? And then we will talk about the final exam. Yes. Okay.